Hello students, so today we are going to discuss a very special topic, that is geometrical isomerism. Now what is geometrical isomerism? It's a type of stereoisomerism. Now what is stereoisomerism? In stereoisomerism we say the particular compounds have same formula and they have same arrangement of atoms, but there is a change in the orientation of atoms in the space. By orientation I mean the position of atom relative to each other in space. Let's just suppose if you have a particular compound which have restricted rotation because of multiple bond like this, and two atoms are connected in this way and two other atoms are connected in this way. Now I will change orientation of at least one side, that is like this. Right, so this represents your geometrical isomerism. Now the similar type of rotational part we can also see in conformers, but in conformers there is free rotation between bonds. If this bond is sigma bond, you will have the free rotation of bonds, right? It can move in any direction. But when this particular bond is multiple bond, specifically speaking double bond, then the rotation is restricted. Why it is restricted? We'll discuss about that. Now geometrical isomerism, for geometrical isomerism, it arises due to restricted rotations. Now where you can see these restricted rotations? In C double bond C, C double bond N, C double bond O, or cyclic compounds like cycloalkanes. All these compounds show geometrical isomerisms due to restricted rotations. Now what is exactly the geometrical isomerism concept? Now when we talk about geometrical isomerism, we say the areal distance between the particles should be different, between the atoms should be different. Now what is the condition for geometrical isomerism? First, as I said, the rotation should be restricted. If we say in C single bond C, C single bond C, this particular carbon is sp3 hybridized and does have a free rotation. It has a free rotation. But when we talk about C double bond C, it will not have a free rotation. It will have a restricted rotation, sp2 hybridized. It will have a restricted rotation. Now, why this rotation is restricted? I'll explain this to you here. Now, when we talk about an sp3 hybridized carbon, this due to axial overlapping is sigma, and there is overlapping that is lateral between pi bonds. So it has electron clouds on both sides, right? Now these electron clouds have to be in same space, as they can only overlap in lateral formation, so they have to be in same space. Now this particular space, if you rotate it by bit, let's just say for example 5 degrees, if you rotate this by 5 degrees, then this particular overlapping would not be possible. One would be like this, another would be like this. So what we have to do, we have only two particular possibilities for that overlapping, that is one, parallel overlapping like this, or rotating one of them by 180 degree and the overlapping like this. This is the only lateral overlapping present due to this presence of electron cloud on both sides, right? This is what we talk about being the rotation being restricted. Now, condition for geometrical isomerism, as I said, first thing first, that the particular rotation should be restricted. Another, that restricted carbon should have different group attached to it. Should have different group attached to it. Now, what about this particular different group attached? I am talking about, like we have carbon double bond carbon, A being attached to B here and C being attached, let's just take it, D being attached to E, right? Where A, B, C, D and E are some different elements. Now, for geometrical isomerism, A should not be equal to B, and similarly D should not be equal to E. All these conditions need to be fulfilled in order to obtain a geometrical isomerism in compounds. Now, what type of compounds can give geometrical isomerism? That is a basic question that arises. Another question is how many types of geometrical isomerism are there? So we'll discuss all of them. First, which of the following compound can show geometrical isomerism? Exhibit GI, that is geometrical isomerism. I would try to cover as many cases as possible in given examples, but we'll have to deal it in somewhat short as we are short of time. Now, which compounds exhibit geometrical isomerism? If I have carbon attached to CH3 and CH3 like this compound, commonly known as butene. Does this show geometrical isomerism? Let's check out. Now, the condition, it has a restricted rotation as it has multiple bond, and we can see two groups attached to this, CH3 and H, and CH3 and H are different. Like I am talking about groups attached to a particular carbon. Don't say that this CH3 and this CH3 is same. They are attached to different carbon. To this carbon, CH3 and H is attached, and this carbon, CH3 and H is attached. They are not the similar groups, so this will show your geometrical isomerism. It will show us the geometrical isomerism, this case, right? Now talk about another case. Let's just talk about this. If we have CH3, C, H, double bond C, we have Cl here and Cl here. You can see I have deliberately made it a different case here, that Cl and Cl are the same group attached to the same carbon. So it will not show any geometrical isomerism. It will not show geometrical isomerism, right? Talking about some different case. Let's just talk about carbon, double bond carbon. Here we can see CH3 attached to Br, H and Cl. All four groups are different. Will this show the geometrical isomerism? Yes, it will also show the geometrical isomerism. If carbon is attached to nitrogen, N would be there, lone pair would be there, and another H would be there, and CH3 would be there. Will this show the geometrical isomerism? Yes, it again shows the geometrical isomerism. Some of the cases are bit controversial and different. You have to talk about them also. Let's just talk about this. If I have a cyclohexane, right, attached to double bond, and we have HCH3. As you can see, these two groups are different. What about this particular carbon? It has a group attached on this side and this side. If you look closely on moving this side or this side, this particular group is the same. So we can say it will not show geometrical isomerism. Why? Because this carbon has same groups attached to it. Now coming on to the similar kind of case. If we have again the cyclic compound and one of them has a substituent like CH3. Now on moving this side, you can see we have CH3H attached to this particular carbon, and we have only hydrogen attached to this carbon. So this makes this group different on both the sides. So it will show geometrical isomerism, right? Just make sure you don't make some silly mistakes here. If such kind of group is attached, consider it as one single group. Now moving from here or here, it doesn't matter if the CH3 is written down or H is written upwards, because it shows the 3D representation of this particular molecule, right? So this is same for the both sides, so it will not show any geometrical isomerism, right? These are the types where we can differentiate between the compounds which can show geometrical isomerism or which do not show the geometrical isomerism. Coming on to the next part, we'll talk about type of geometrical isomerism. The first part is the cis-trans isomerism. a quick detail, we would say cis represents same groups being on same side, and trans represents same groups on different sides. Now, we would say this particular concept where same groups are on same side, it is known as cis, and same group are on different sides, it is known as trans. Let's just take an example for this. If I talk about this particular group having CH3 as the attached group which is on the same side and HH on different side, then this represents a cis isomer. Whereas trans isomer can be drawn like this, where CH3 and CH3, the same groups are on different side. This would be your trans group, right? Is that understood? Now, coming on to the next example, we can say if even one group is there which can be the same, like H and H here. If the H and H group being the same is on different side, it would be trans, and if it is on the same side, it would be cis, right? This is a short example of a cis trans isomer. So I'll cover the next topic, then we'll move back to cis trans isomer and cover some more examples.